So, good evening, everyone. This is the last session on fundamentals of electronic materials and devices. So, the past 8 weeks, we had been discussing the weekly contents and we had been solving problems related to that. So, hello. So, is the screen visible to all of you? Can anybody please confirm?
Yes, ma'am, visible.
Yeah, so for the past 8 weeks, we have been discussing topics related to fundamentals of electronic materials and devices, and this will be the last session. And on 24th, you will be having your examination. I think somebody just messaged. So I prefer that you unmute and speak because otherwise I'll have to switch between the windows to come and see. So in this class, we won't be discussing any concepts. What we are going to do is we'll be seeing a few questions and I'll be displaying the questions on the screen and you're supposed to solve the questions and answer. Like for the same purpose, you'll have to use the virtual calculator as well as the formula sheet that was uploaded in the SWAYAM portal. So are the instructions clear?
Yes, ma'am, clear.
Yeah. So in that note, let us start the practice question. So we'll be covering all the topics starting from week 1 till week 8. So if you have gone through whatever sessions I had been doing the previous weeks, you'll be able to answer fairly well, I think. So the first question is, what is the density of states, that is GE, of a free electron gas metal and an energy of 3 electron volt? You have to give your answers in units of joule inverse meter power minus 3. So you'll have to go through the formula sheet, find out the equation for density of states, given that the energy is 3 electron volt. And one thing you have to note here is that you have to convert the 3 electron volt into joules. That is because if you see the final part, you'll see here that the final answer is in joules and joule inverse per meter cube. So can you please start solving? And once you get the answers out of this option, please let me know. So please start solving. Hello. From the formula sheet, please find the equation for G of E. And once you get the G of E, all other values and units will already be there in the formula sheet. You have to just substitute and you'll get the answer. Please try.
Yes, ma'am, I try.
Yeah, sure. Yeah, so have you started getting any part of it? Like this is the equation that you have to substitute. So here you have only three things. One is the mass of the electron, then other is the h cube, that's a constant, and then we have root of ef, which is the work function of the material. Work function of the material is given, or the energy is given here as 3 electron volt, and that has to be converted into joules. So if you have substituted in the correct way, can I know what is the answer that you've got?
My answer is 7 point into 10 to the power 46.
Okay, so if you are 7.3 into 10 to the power 46 is the right answer.
Yes, ma'am. That's all.
Yeah. So this is the second question. The resistance of a copper wire is given as 2 milliohms. Length of the wire and dia of the wire is given. So what is the resistivity? It's a very simple direct problem. You just need to know the equation that connects resistivity and resistance. It's a very basic problem. Yeah, like please note down the values. Resistance is 2 milliohms, wire length is 10 centimeter, and dia is 1 millimeter. What is the resistivity? And you have to give the resistivity value in nano ohm meter. Yeah, so the resistance is given, length of the wire is given, and the dia is also given. You have to find the resistivity. Now, once you've calculated, please unmute and give the answer.
Okay, ma'am.
Yeah.
My answer is B.
Okay, let me check. Answer is B. Yes, 15.7 nanometer will be the answer. So
Okay, ma'am.
15.7 nanometer. Yeah. So next is, what are the probabilities of an electron occupying an energy level that is 0.01 eV above EF, that is the Fermi level energy, at 300 Kelvin and 500 Kelvin respectively. So from the formula sheet, you'll have to look at an equation which connects E and EF. That is, there are equations which has the term E minus EF and EF minus E, right? Yeah. So using that equation, you'll have to find out the probability of an electron occupying the given energy level. That is 0.01 electron volt above the Fermi level at 300 Kelvin and 500 Kelvin. So you'll get two values and in order what is the option according to the question. So that is the one you have to answer.
Ma'am, electron volt is converted to joule.
Yeah, you'll have to convert.
Okay.
And the constants you'll have to substitute accordingly. Suppose you have here it is given 0.01 electron volt, right? So the K value you will have to substitute in like if you are substituting this in electron volt means K also you'll have to substitute in electron volt. But if you are substituting K in joules, you'll have to convert this E value also to joules. And in the formula sheet, K is given in terms of joules, I think. Therefore, it's better to convert the electron volt here itself.
Ma'am, at the 300 Kelvin,
Yes.
answer is 0.44.
Okay.
Answer is D.
0.44 at 300 Kelvin is 0.404 and at 500 Kelvin it is 0.44. So it will be 0.41 and 44, right?
Okay.
Yeah. Like where did the substitution go wrong? Only one value will change, the temperature. Rest everything will be same. So E minus EF is 0.01. We are converting that into electron volt into joule. Then 1.38 into 10 power minus 23. And in one case you have to substitute 300. In one case you have to substitute 500. Only that difference is there. Rest everything remains the same. So
Okay.
0.44, yeah, we have an option here. 0.4045, we'll round it to 0.41. So C will be your answer. Yeah,
Okay, ma'am.
yeah. So I hope this is clear. That is one is 0.41 and the other answer is 0.44. Yeah. So next is the band gap of an intrinsic gallium arsenide semiconductor is 1.43 electron volt. Its electron affinity or chi value is 4.07 electron volt. Assuming that the effective mass of electrons and holes are same, what is the work function of the material? Here they have asked for the EG value. Band gap is given. No, they have given the band gap. That is EG value is given. You have to find out the phi value. That is work function. So band gap is given. Psi value
And
is
that is
given. Yeah.
EF value, ma'am.
Yeah.
Okay.
Phi value you have to find out. Phi. So in that kind of questions, it is better to draw the band diagram and then start.
My answer is C 4.78.
Okay, let us see. So 4.785 is the final answer. Yes.
Okay.
Yeah. That is, I hope it's clear. Yeah. So next is two semiconductors X and Y have the same effective density of states, that is Nc and Nb are same. The intrinsic carrier concentration of these two at X and Y, that is at 300 Kelvin are 2 into 10 power 13 and 10 power 10 less respectively. So if the band gap of X is given as zero point 0.7, then you have to find the band gap of Y. So Nc is equal to Nb is given. Intrinsic carrier concentration of both of them at at a particular temperature is also given. If the band gap of one of them is zero point 0.7, then what is the band gap of another? You have to use the equation for which connects Nc, Nb, intrinsic carrier concentration and temperature, and you have to take the ratio. So if you take the ratio, you will be getting the band gap of Y. So can you please try?
Okay, ma'am, I try.
Yeah. Yeah, so have you taken the ratio?
Yes, ma'am.
Yeah, so basically you have to use Ni is equal to root of Nc Nv into e power minus Eg by 2 times Kd. And out of this, Nc N1 and N2 is given, like one is 2 into 10 power 13, other is 10 power 10. And Eg1 is also given. Now what you have to do is you have to take the ratio Ni1 by Ni2, and since Nc1 and Nv are equal in both 1 and 2, those terms will get cancelled. Only what will remain is e power minus Eg1 by 2 times Kt and e power minus Eg2 by 2 times Kt. So rest all values are given. So if you substitute that, then it goes like this, and only value that is remaining is minus Eg2. So have you reached till this substitution? Yeah. Hello.
Yes, ma'am.
Yeah. So up until the substitution, if you are getting, it's only a matter of solving. You'll have to find Eg2, and since it is e power something, what you have to do is you have to substitute ln on both sides, and ln e of something will become that constant itself. For example, ln e power minus Eg by 2 times Kt is basically Eg by 2 times Kt. So if you, yeah, yeah, substitute like that, you'll finally get the Eg value. Yeah, somebody texted, I think. Let me check. Okay. Somebody has joined now. So if you see, this is the substitution. So if you see here, this is Eg by 2 times Kt, and you'll have a constant here, and in order to remove that, you'll have to take ln on both sides. Finally, you'll get the Eg value. It is approximately 1.1 electron volt. So that is the answer that you're supposed to get. Was that clear?
Yes, ma'am.
The next is the intrinsic carrier concentration of silicon at 300 Kelvin, that is Ni value is given. Electron and hole mobilities are given mu E and mu H are given as 1350 and 450. So if silicon is doped with 10 power 15 phosphorus atoms at 300 Kelvin, and the dopants are completely ionized, means that there are no residues, you have to take n value as 10 power 15. Then we have to find out what is the electrical conductivity of the doped silicon at this temperature. So it's direct substitution. Only thing is, so if you see here, intrinsic carrier concentration Ni is given, mu E and mu H are given, also n value is given, 10 power 15. First, you have to find the P value, and once you get the P value, you'll have to find the electrical conductivity. So, two equations. One is Ni square is equal to Np, and next is the equation for conductivity. So, if you use both of them, you'll be able to answer. So, please try. So if you got an idea, basically n is given, mu e mu h is given. So first you have to find out p, that is ni square by n. So have you got the value of p as 10 power 4? Have you tried? Ni square by n will give you the new p value. So intrinsic carrier concentration is known to us, dopant concentration is also known, and then you get p. So once you get p, you will have to use the equation sigma is equal to Ne mu e plus Pe mu h. So if you substitute that, what will be the answer? So have you substituted?
Yes, ma'am. I substitute.
And what is the answer?
Ma'am, answer is B 0.216.
Okay, so you said answer is?
B 0.216.
Yeah, 0.216 is the answer. So next is calculate the width of the depletion region for a germanium d-n junction. Acceptor concentration or Na is given as 10 power 16. Donor concentration or Nd is given as 10 power 18. Intrinsic carrier concentration Ni is 2.4 into 10 power 13. You have to take the temperature to be 300 Kelvin and the relative permittivity of germanium to be 16. So first you have to find the voltage, and then from the voltage you have to find out the width of the depletion region. So all the other values are given. Epsilon 0, it is given in the formula sheet. Epsilon r is given to you. Epsilon is basically equal to, if you know the equation, epsilon r is equal to epsilon by epsilon 0, right? So epsilon value will be epsilon 0 into epsilon r. So both of the values are given to you. So using, and like rest all are given, first you have to find the voltage and then the depletion width. So please attempt and let me know.
Yes. Ma'am, answer approx 427.53.
0.5. Let me check. Because the
4 to
voltage value is 0.43. Is that correct? V0 value will get us 0.43.
no, ma'am.
Okay, where did the substitution go wrong? First KT 1.38, then E 1.6 into 10 power minus 19, then Na and D by Ni square. Na is 10 power 24, and here what you have to do is you have to convert everything into m power minus, or final, what is the answer you got? In case you are doing in centimeter, final answer also you'll get like that. There will be a difference in voltage, but it's better to convert to meter and then do, so that everything will be in standard units. Final value is 0.28 micrometers.
Okay, ma'am.
Yeah. So where have you done mistake? Like, have you realized which is the difference?
Yes, ma'am.
Yeah, so maybe that conversion part you might have not done. So next is, consider a Schottky junction diode between AU and N-type Si with 10 power 16 donors. The electron affinity of the silicon is given as 4.01, and the work function phi of AU is given as 5. If Ni is equal to 10 power 10 and the band gap of silicon is 1.1, what is the built-in potential? And one more condition is Nc is equal to Np. They are asking the built-in potential that is formed between a Schottky junction between Au and N times Si. The number of donors, the electron affinity, and work function of respectively all of them are given. So in that case, what is the built-in potential? initially you have the intrinsic carrier concentration given by Ni is equal to root of Nc Nv e power minus Eg by 2 times Kt. And Nc is equal to Nv is already given to you. And then what you have to do is you have to substitute this Nc is equal to Nv and Eg is equal to 1.1 for silicon. And finally you will get the Nc value as 1.78 into 10 to the power minus 19. Once you get Nc, we mean that we also have the Nv value. Now you have to find out the same thing for the Au part. So this much is like, are you getting Nc is equal to 1.738? Hello? Ni is given to you, Nc, Nv are equal. That condition is also given. You have to substitute Eg as 1.1 for silicon and you will get the value of Nc and Nv. Here it is also given that Nc is equal to Nv. So next time what happens is in this part, when you substitute, it becomes Nc into Nc and there will be a root. Therefore, it becomes Nc square, root of Nc square and it becomes Nc alone. And using that, you have to find the next set. So then what happens in an n-type semiconductor, we can again write n is equal to Nc because before, like I said, root of Nc into Nc becomes Nc alone, e power Ec minus EFn by Kb into T. That is the relationship between the Fermi level and the conduction band energy. And if we substitute Nc value, we know n is given to us, it was 10 power 16. And Nc also we had found out this Ec minus EFn value we have got, which means that the Ec is actually above the Fermi level. So if the Fermi level is on top, after 0.19286 electron volt, you will reach your Fermi level. So that difference is there. So Ec minus EFn part you will get. And built-in potential in Schottky is given by EV0, which is equal to phi m minus, that is work function of the metal minus work function of the semiconductor. And work function of the semiconductor, as I have already discussed, can be written as psi semiconductor, that is the affinity of the semiconductor, plus Ec minus EFn, which we have already found out. And this value is also given to you. And phi m also is also given to you. That 5m was given as 5 electron volt and psi of the semiconductor was 4.01, and Ec minus EFn you have already got as 0.19286. So finally your V0 value will be 0.797 volt. So is it clear on how to approach this problem? What is the crux of the problem? Have you understood? Yeah, like we had already solved in class this question. So if you want a detailed explanation of the same, please go through the lectures that I've already conducted. This is just a revision part. So just a reminder on how to approach this problem. So initially a condition was given that Nc is equal to Nv and Ni value was given, and from there you could find the Nc value. And then later you substitute the same Nc to find out Ec minus EFn. And once you get Ec minus EFn, whatever you need to find, the built-in potential is already given to you. That is work function of the metal and the affinity of the semiconductor. And if all of these things are given, finally you will get EV0 as phi m minus psi semiconductor plus Ec minus EFn. And you'll get your V0 as 0.797 volt. Is that clear?
Ma'am, what is the n value?
N value. So here you have n is equal to Nc, right? So the n value, let me go back. Yeah, n value is given as 10 power 16. an N-type semiconductor with 10 power 16 donors are given. So that is your N value.
Okay.
Yeah. So next is a kind of a descriptive problem. It's a logical answer that you have to give. Consider an N-type silicon with 10 power 17 donors per centimeter cube. Electron affinity is given as 4.01. Work function of four metals, cesium, lithium, aluminium, and gold are given as so and so values. Suppose S for silicon, Eg is equal to 1.10. Ni is equal to 10 power 10 and EFI is equal to 0.55. We have to choose. So silicon is the semiconductor material and we have another four metals also here. We have to tell which of the metals will form a Schottky junction and which of the metals will form an ohmic junction. So for that you have to find out the work function. And for finding the work function, what all you need is already given to you. Eg is there, Ni is there, EFI is there. So using that, first you find the work function and then you compare the work function of our silicon with the work function that is given here. So after evaluating, you will get which of them will form Schottky junction and which of them will form an ohmic junction. Yeah. So please first find the work function of silicon and then compare the values. So have you got the value of work function of silicon as 4.14 electron volt? Hello?
Yes, ma'am.
Yeah. So once you get 4.14 electron volt, if you compare AL and AU, one is 4.25 and one is 5 electron volt. And if the work function of the semiconductor is less than that of the metal, they'll form a Schottky junction. While in case of cesium and lithium, it is 1.8 and 2.5, which is less than the semiconductor, which is less than the semiconductor. So if metal work function value is less than semiconductor, it will go and form an ohmic junction. So the answer would be option C. Yeah. So next is germanium PN junction diode at T is equal to 300 Kelvin has Na is equal to 10 power 18, Nd is equal to 10 power 16, dH is equal to 49 centimeter square per second, DE is equal to 100 centimeter square per second, tau E is equal to 2H as 5 microseconds, and A is 10 power minus 2 centimeter square. So we are asked to find the reverse saturation current density. The Ni value is given as 2.4 into 10 power 13. So here you have to calculate the reverse saturation current density. So equation for finding reverse saturation current density is already there in your formula sheet. So, and whatever is required for finding out is already given. So you can do a substitution and find out.
And that is J naught value.
Sorry?
J naught value, ma'am.
Mm,
Reverse saturation density.
huh?
J naught.
J.
Okay.
What is meant by J? I am not getting what is it?
Ma'am, reverse saturation current density is
Huh?
J, formula is given J naught equal to Ni square E.
Yeah, same one, same one.
Okay.
Yeah. So J naught value is given as E n I square dH by LH ND plus DE LE NA, and LE and LH you have to find out root of DE tau E and DH tau H. So substitute all those things, you'll directly get the value.
Ma'am, answer is C, 2.9 into 10 to the power minus 5.
Yes, yeah, that's the answer. 2.9 into 10 to the power minus 5 is the answer. So this is the reverse saturation current density. Suppose they are asking the forward current density, there will be a small change to this equation. So if you see here, now they are asking same detail, same everything. They are asking to determine the current density for a forward bias voltage of 0.3. So only small addition will be there to that J0 equation. You will have to add e power EV by kBT minus 1. So is that clear? If only reverse saturation part is there, only initial part. If they are asking for a forward current density, we have to add the e power EV by kBT minus 1 value to the equation. Rest everything is same. Substitution is also same only.
Yes, ma'am, that is true.
Yeah. So next is choose the correct option for an N-type MOSFET under normal operations. N, ND, P represent electron concentration, donor concentration, and hole concentration respectively. So like the previously discussion was going on, there are no equations in the formula sheet from MOSFETs and JFETs and so on. So most probably from those areas you will be getting this kind of descriptive type of questions. So be very clear with the concept part. Problem wise, I think most probably you won't be getting any problems from that area. So better to go for the logical part. So here they have asking N-type MOSFET is there. Under normal operation, what is the relationship between N, ND and P? So this is an N-type. So in inversion region, it will be anyway P greater than N, right? So you have two options. From that two options, you have to tell me which is correct. Initially, it is an N-type MOSFET. So in the inversion regime, what happens is that the N gets inverted into P. So initially, you can eliminate two options, and from the remaining options, you can select the right answer.
Ma'am, please explain the answer.
Yeah. So basically, In case of a MOSFET, what happens is that initially it is an N-type MOSFET. N-type MOSFET means that bulk of the material has more number of electrons than holes. Therefore, in bulk, N will be equal to Nd. That is the donor concentration. That is for an N-type material. In depletion region, what happens? The number of electrons will start reducing, but still it will be, what happens, the number of electrons will start reducing, but still it will be greater. So if you see the second line here, so what happens is the N inside the depletion region will be less than Nd because it is going towards the p type, but still it will be greater than p. So initially you have a material which is N type, which means that it has large number of donors, therefore N is equal to Nd. So as the potential goes on, what happens is the depletion region gets formed, and in the depletion region the carrier concentration will be less than the donor concentration but will be greater than the number of holes. So eventually in a MOSFET, what happens? In the inversion region, the N-type MOSFET gets converted in that particular region to P-type. That is, the number of holes will become greater than N. Therefore, we can say in bulk it is Nd. In depletion region, it is somewhat between Nd and P, and in the inversion region, it becomes less than P. So that is the normal, it comes from the basic definition of MOSFET. Under normal operation, what happens in a MOSFET. So I hope it's clear. Yeah. So we have explained how this actually works, like how the MOSFET works, how the depletion region is formed, what happens during inversion, all these things have been explained. So if you get time, please go through the video. So basically in the bulk it was N-type, in the inversion it gets ulta, that is it becomes P, and in the depletion region it is somewhat intermediate. It hasn't become P, but it has lost a large number of electrons. Yeah. So next is zinc selenide in hexagonal form is a direct bandgap semiconductor with bandgap value of 3.9. Assuming ideal crystal, portion of the electromagnetic spectrum where emission lies is dash. So you know the bandgap value. So based on the bandgap value, you will have to calculate the wavelength. Once you calculate the wavelength, you have to say which part of the spectrum it lies in, whether that wavelength is IR, visible, UV, or X-ray. It's a rather direct question. So first you have to find out the lambda value. So there was a relationship that I told in last class between the Eg and lambda value. If anyone remembers, it is Eg or E is equal to 1240 by lambda. So you will get the lambda in nanometer. So can anybody tell me what is the lambda value that you get? Can anybody tell me the lambda value? You have to substitute 3.9 is equal to 1240 by lambda, or lambda is equal to 1240 divided by 3.9. 1240 by 3.9. 1240 is actually a shortcut for HC, the constants H and C. If you multiply, you will get 1240. So if you get that, you will get the lambda value. Can anybody tell me what is the lambda value?
Ma'am, 317.9.
Yeah, and 317.9, what is the spectrum? Like, is it visible, UV, IR, or X-ray? It's anyway not X-ray, so it is not IR. So is it visible or UV? If you see the electromagnetic spectrum,
And that is a visible.
visible starts at 400, right?
Yeah, like,
UV.
UV, yes, exactly. So it's 317.94 nanometers, and that lies in the UV part. Therefore, the answer is UV. So this is the actual equation, E is equal to hc by lambda. In that, h and c are constants. So if you multiply them, you'll get 1240. This is the shortcut. But you have to keep in your mind, then lambda will be in nanometer, E will be in electron volt. Suppose in question it is in joule or some other unit, please remember that to substitute 1240, it has to be in lambda, that is in nanometer, and E in electron volt. Otherwise, you'll have to convert and then substitute. So I hope that's clear. So next is light of wavelength 550 nanometer and intensity 1 megawatt is incident on a surface. We have to convert it into number of photons per second. So wavelength is given, intensity is given. We have to convert it into number of photons per second. And photons per second is basically second inverse. It's a number per second, right? So particularly number means it's just a count, it doesn't have a unit, and it's per second, therefore second inverse. So wavelength is given, intensity is also given. So how do you convert it into photons per second? So can you try or should I explain?
Give us hints, ma'am.
So basically you'll have to convert the wavelength to energy, then you'll have to relate it with the intensity and find the counts. E is equal to hc by lambda, we know, right? That is the energy of one photon. So you'll get the energy of one photon. You know the intensity is megawatt, which means that it is a power unit. Power basically means work done or energy per sec per time, right? So based on that, you will have to convert. So E is equal to hc by lambda, we know. So basically 1240 by 550 you'll do, and you'll get 2.5 electron volt. That is the energy of one photon. And for intensity, basically it means the number of photons into energy of one photon per unit area per unit time. That is basically it's a power unit. And suppose we are considering that AT is equal to 1 per unit area per unit time. We have I is equal to N into E, and N is therefore I by E. So here I is given as milliwatts, that is divided by 100.001, and this energy value you will have to convert it into joules since it is watt. So that is 2 point whatever you got, 2.25 whatever into 1.6 into 10 power minus 19. So you will get number of photons as 3 into 10 power 50. So is that clear?
Yes, ma'am.
Yeah. So next is the open circuit voltage of a PN junction solar cell is 0.45 when the photocurrent is 50 milliamps per centimeter square. What is the open circuit voltage when it is increased to 500 milliamps per centimeter square? Take temperature to be 300 Kelvin and all other device parameters are the same. We have to, that equation is directly given in the formula sheet, so you can substitute and try. So have you started substitution?
Yes, ma'am. Doing
Yeah,
it.
yeah, sure.
Ma'am, 0.45.
0.45. Okay, so is this the equation?
Yes, ma'am.
Okay, and VOC is equal to 0.45 initially, and now we have to find out the ISO value, and 0.45 is the first case, right? Now you have to find out when it is increased to 500 m centimeter square. So initially VOC is equal to kb by ET ln IPH by ISO. IPH is given as 50, so you will get VOC. So, and VOC is given, you will get the ISO value. And this ISO value, you will have to substitute in the new one so as to get the new VOC value. So, is that clear? So the initial part is already given to you, right? 0.45. 0.45 is given, KB is known, T is known, E is there. There is only one ln, this is a typo. Then IPH is given. Only thing that we don't know here is the ISO value. So first we calculate the ISO value, that is 1.4 into 10 power 9. And that ISO you will have to substitute in the second set. And their IPH was increased to 500 microamps per centimeter square. So new VOC is 0.55. Is that clear?
Yes, yes, ma'am.
Yeah. So next is consider an N-type silicon with a dopant concentration of 5 into 10 power 15. It's illuminated with light that creates 10 power 21 electron hole pairs per second. Minority carrier lifetime is 50 nanoseconds at steady state. What is the ratio of hole to electron concentration? Ni is initially 10 power 10. So this thing we had discussed recently, if you remember, it was discussed in 1 week or maybe 2 weeks before. So I think it will be kind of more easy to recall compared to the previous content. So are you able to attempt or should I explain?
Explain it now.
So basically they are telling initially we have an n-type material. It has Nd is equal to N is equal to 5 into 10 power 15. When light is shining, basically, in addition to this 5 into 10 power 15, more carriers will be created. And this more carriers, they have given 10 power 21 electron hole pairs per centimeter cube per second. And minority carrier lifetime is 50 nanoseconds. So since this is per second, we have to multiply it with the lifetime. That will become, if we multiply 5 into 10 power 13, that is delta P. Your new number of carriers generated is 10 power 21 into 50 into 10 power minus 9. That is 5 into 10 power 13 is the excess carriers that are generated. So new electron concentration will be initially what was there, 5 into 10 power 15 plus the delta N. That is 5 into 10 power 15 plus 5 into 10 power 30. It will be approximately equal to 5 into 10 power 15 if you add. Now, new hole concentration, how will you find out? You have to find out Ni square by Nd plus delta P. Ni square is already given to you, that is Ni is equal to 10 power 10. So, Ni square you can find out. Nd is also given to you plus delta P, that is the new one. If you substitute this, this also will come as 5 into 10 power 30. And now you can just find the ratio of the P by N, that is equal to 10 power minus 2. So is that clear? So initially you have a particular amount of electrons and holes, and when you shine light on top of that, what happens is that new carriers will be generated. Now they have asked us to find out the ratio of the new total concentration of electrons to the new total concentration of holes. Is that clear?
Okay, ma'am. Yes.
Yeah. Yeah. So next is arrange the following semiconductors in the order of increasing wavelength of emitted light during recombination. They are all direct band gap semiconductors. So this is more of like either you have to memorize the values or you'll have to just have an intuition. If you even if you don't know the actual value, just remember the order. It will depend on the band gap. So first you
Excuse me, ma'am.
yeah, sure.
Show me the previous slide one more time.
Yeah.
Previous. Just a minute.
Yeah. All of these material, whatever I'm using here, it is already uploaded in T-SWAYAM portal. There will be a drive link. In that drive link,
Oh,
all the PPTs are already uploaded. So you can
okay.
just download and use them.
Thank you, ma'am.
Yeah, yeah. So here we know that, so first, since you don't know the values, I'll start is gallium arsenide, it is 1.42, cadmium selenide is 1.47, and zinc oxide is 3.37. So 1.42, 1.47, 3.37. So we know that if you take 1 to 40 by lambda, this order will come in the inverse way, right? So energy of light you have to find out in the increasing order of wavelength. Increasing order of wavelength means the smallest one has to come first and smallest one will be the reverse. So Eg is given. From Eg you have to find out the lambda value, and the lambda value then you have to arrange in the increasing order. So if you don't remember the actual values, please try to keep the order in mind. Gallium arsenide, cadmium selenide, zinc oxide. Zinc oxide will be maximum, gallium arsenide will be minimum. So is that clear?
Yes, ma'am.
Yeah. So wavelength wise, it will be the reverse. Zinc oxide will be the least one and gallium arsenide will be the maximum. So whatever is there in Eg, it will become ulta when you write the lambda value. That is the only thing. Yeah. So that is all. So this was a very simple recap session. So I hope it was useful for all of you. And you have your examination on 24th, right?
Yes, ma'am.
Yeah. So prepare well and go through the assignment questions, practice assignments, everything, whatever we have practiced. And if you get time, go through the videos also. But since it is only 2-3 days away, just keep on focusing on the assignments, concepts, everything. Be comfortable with the virtual calculator as well as the formula sheet. So I hope all of you do well. All the very best, and thank you very much for joining my sessions. Yes. Yeah.
What is the percentage of problems there in all?
That won't be a fixed value. It can be highly
Oh.
variable. But one general thing is initial part will have more numericals and later on it will go into conceptual part. MOSFETs, JFETs, light related things, those will be predominantly theory and numericals will be from the initial sections. Usually it is like that, but it will depend on your luck. Yeah.
Thank you.
Yeah. Yeah. So I hope that's all. I think all the very best and do your exams well.
Thank
Yeah,
you.
thank you very much for joining, both of you.
Thank you.
Yeah, thank you so much.